Hey guys, we're going to talk about the normal distribution and the binomial distribution kind of together. So this is our 8.1 day 2 for the binomial distribution. We're looking at page 9 in our packets, and we're going to forego the warm-ups for the video. And so we're going to talk about can we use the normal distribution and why might we use the normal distribution to approximate the binomial distribution. So one of the things you'll notice as we have the number of trials increasing, our overall distribution of successes is going to start looking more and more like the normal distribution. So if we look at this little graph here, if we only have up to 3 trials, we kind of can see the normal distribution in there. But as n gets larger, our actual distribution, which is this little set of histograms here, will be closer and closer to normal distribution until the fact where n approaches infinity. Then we start becoming actually normal. Now, we can't really have an infinite number of trials, not in the real sense of things, but you can see as the number increases, the actual probability curve will get closer and closer to a perfect normal distribution. And if you want to see this a little bit more carefully, you can take what we did with the last video and make that histogram and increase your number of trials and see what happens. Okay, so let's see what we get. So flip the page over. And we've got a particular just beginning problem here. So let's say we're looking at the ACT. And the math proportion of the ACT is 60 questions. There's 5 possible answers for each question. What's the probability of a student guessing at most 10 questions correctly? So we're going to let x equal the count of correct answers. And we're looking for the probability that you get x to be, well, at most 10, which means 9876, right? Less than or equal to 10. So how do we figure that out? So if we do this as a binomial problem, first thing is there are 2 solutions. It's either correct or not correct, so it's that. Each probability is the same. There is a set number of questions, set number of trials, that's our 60, and each one is independent. So this is binomial, and our average, our number of trials is 60. And our probability of success is 1 out of 5. So x is binomially distributed with that. And so how do we actually figure this out? So what can we do? Now on the AP exam, if you say this, you can basically turn this into a number. So you have to tell them it's binomial, you have to tell them the number, you have to tell them the probability. How do we get at this number? Now if we're doing this straightforward by hand, which I'd like you to try doing, we're adding up everything from 0 to 10. So we're doing the sum from x equals 0 to 10. And what do we have? Well, we have n choose x, right? So we have 10 and we're choosing certain numbers. We have 60. We have 60 different things, and we're choosing numbers from 0 to 10 out of that. So n choose our x and choose r. And then how many successes are we going to have? So the success is 1 out of 5, or 0.2. And how many of those are we going to have? We're going to have x successes. And our failure happens 80% of the time. And how many failures are we going to have? So if we have 0 successes, that doesn't mean 10 failures. That means, well, n failures. So we have our 60 minus x. So there is no way that I would type this in my calculator, but I mean, some people actually choose to do so because they don't mind the notation and they like seeing that they get it. But if they don't see that, this is also equal to our binomial CDF. And so what do we need? We need our number of trials, so 60. We need our probability, which is 1/5. We need our number, which is 10, and it's always inclusive when we do the binomial CDF. So this would be the same thing. Now here's the part here's why we would use the normal distribution instead. So this 60 choose anything? How do we do 60 choose, let's say 5? So that's 60 factorial divided by, okay, so we're picking 5 of those. So I don't care what order those 5 are in, and I also don't care what order the other 55 are in. If you really want to figure out what 60 factorial is, now 60 factorial over 55 factorial is actually a little bit better. Let's say we're doing something like 60 choose 20. And we have 60 factorial, and on the bottom, we've got 20 things that we're choosing, and I don't care what order those are in. And we have another 40 of these that we're choosing, and I don't care what order those are in. Are you going to want to do this by hand? Like, even on a calculator, you can start running into problems. So, like, 60 factorial is not outside, your calculator's realm of possibility. I can do 60 choose 20. But let's say I'm going to do something a little bit bigger. Let's say I want to do 150, and we want to choose let's say 55 of those. I start to run out of space here. Actually, I was surprised that didn't overflow me. So let me try this 100, and let's make it even bigger. Let's make it 200 choose 55. No, haven't overflowed my calculator yet. Let's try 200 choose, I think 100. It's getting bigger. But one of the things that you're going to realize is you get these numbers that are so huge that you can't handle them. And actually, if you have a really big number, you can actually overflow your calculator. So this may be something, that you might not actually be able to do. Now, you do have a calculator. Your calculator can handle these numbers, so let's at least find the answer to this problem so that when we do it a different way, we've got it. So I cancel my calculator, of course. So you should pause this and go through, or try to do this while it's coming up. So go there, and we need to do second distribution, binomial PDF, or CDF, which is here. So it means cumulative. We have 60 trials. We have a probability of success of 1/5, and we want this to be less than or equal to 10. So we have a 32% chance of getting at most 10 questions correct. Okay, so now while this is not a big problem, we could run into big issues, especially if our calculator runs out on us. So what in the world do you do if we don't have the calculator? So we can also use a normal distribution. So one thing that you need to do is you need to check to make sure that you can use the normal distribution. So what we have to do is we have to make sure that n times p is greater than or equal to 10, and then n times q, or 1 minus p, is greater than or equal to 10. So this is, we need to make sure we have at least 10 successes and 10 failures. Or in this case, are expected. Because you haven't really done the test, so you don't know how many successes and how many failures you are. You can just expect to see some successes, and you can expect to see some failures. So n times p, this is also the mean, right? All right, expected number of successes, that would be my expected value. So let's see, what do we get? We have 60 times 1 out of 5. So this is 12, which is at least 10. So I expect 12, right? And then my probability of failure would be, well, n times q, so 60 times 4 out of 5. But to tell you the truth, if there are 12 expected successes, how many expected failures are there going to be? There should be 48 expected failures, which is also greater than or equal to 10. So these are the checks that we have to do. So this has to be true. Now, why does this have to be true? Let's say, how can we say something is normally distributed if I only expect to see like 5 successes or failures? So let's say that we're talking about test scores, and we're saying they're distributed with an average of 98 and a standard deviation of 2. So this is going to be too close to 100% for this to be normally distributed. You can still have it be that, it just would be skewed to the left. Like, it'd be too close to 100% for you to say that it would be normally distributed. So it can't be. So if my mean is here and my max is here, I can't use the normal distribution. Okay? So let's see, what do we get? What else do we know? So we can say that x is approximately normally distributed with a mean of 12 and a standard deviation of, okay, so what was the standard deviation? Well, the standard deviation would be the square root of NPQ, right? So in this case, it would equal the square root of 60 times 1/5 times 4/5. So we have to figure that out. So let's grab that. Square root of 60 times 0.2 times 0.8. So we have a standard deviation of 3.098. So 3.098. So we want to figure out the probability of getting x to be less than or equal to 10, right? So we're looking for probability that x is less than or equal to 10. Now if we're using the normal distribution, we can find the z-score, which equals probably getting a z-score less than or equal to, well, the z-score for this would be 10 minus the average, which is 12, over the standard deviation of 3.098. So once I know what the mean is, which is 12, and I know my standard deviation, which is 3.098, and again the mean is n times p. So once I know the mean, once I know the standard deviation, and I fit these two conditions, that I have enough successes and enough failures, which is at least 10 of them, if those are both true, then I can go to my z-scores. And so now think about this. I can do this in my head for the most part. -2 over 3.098. I don't need to do any crazy combinations. I just have to figure out what this fraction is. And then once we do, we can do the normal distribution. So I need to figure out what -2 over 3.098 is, and that would be my z-score. So sorry, this is not equal to this. So what I'm missing here is I need a probability of a z-score being greater than or equal to this thing. So this equals the probability. So let's figure out what that probability has to be. I'm going to cheat just a little bit here. So there's my numbers here. So I'm just pulling out my answer key instead of redoing this all in the calculator. And so this is kind of where we are. So we go to the calculator and we find our z-score and we do our normal CDF from this to the left. So normal CDF from -1,000 to our z-score that we just found, and we get 0.259. Now I'm not a huge fan of this because is it really all that close to the answer we got by doing it the binomial way? I got my 0.323. You know, and you could argue that this is like 25% and 32%. Like that's 8 percentage points off, basically, or hold on, 7 percentage points off, and this is 0.6 to like 6 percentage points off. So sorry, I can't even add. But that's a decently different answer. Now, which one is exactly correct? The binomial one is the one that's correct. Okay, this is exactly right. We're not doing any estimating. When you use the normal distribution, remember we have basically all these 60 little boxes going on in this problem, right? These are not 60, but you know, you get the idea. And we're using a normal curve to estimate it. So there's going to be all of these little areas in here that are going to be incorrect. On the AP exam, you can go either way, but if you're going to use the normal distribution, you have to show that you have to check these conditions. You have to state that you're using a normal distribution, or they have to tell you you're using a normal distribution. You have to go through the z-score formulas, and then they will accept your different answer if you do this correctly. So I want you to try the other two. If you get stuck, then check my answers on Schoology.